Hey everyone, today we're going to start section 4.5 on integration by substitution. The purpose of today's lesson is to tackle some problems that we can't just rewrite and use the power rule for. Right? In other words, we're going to be tackling some problems that are going to ask us to integrate composite functions. So first, our theorem, antidifferentiation of a composite function. And it gets kind of wordy, but you know that once we get into the examples, it will begin to make more sense. So our theorem, let g be a function whose range is in interval I, and let f be a function that is continuous on that same interval. If g is differentiable on its domain, and capital F is the antiderivative of function f on I, then the antiderivative of f of g of x times g prime of x dx will be equal to capital F of g of x plus c. So in other words, if you take a look, here is where the chain rule is happening. Okay. All right. So like I mentioned, this is a way to undo the chain rule. So we're going to do something called a U substitution. And as you're working through the problems, you're going to notice that one part is going to be easily recognized as the derivative of another piece of the problem. Okay. All right, so a little more notation to get through, and then we'll get into our first example. So it says if u is equal to g of x, then the derivative of u would be equal to g prime of x dx. Okay, and the antiderivative of f of u du would be equal to capital F, like our original function, of u plus c. Okay, in our first example, we want to look for the piece that appears to be the derivative of the other piece. So let's take a look. Okay, so if we take a look, I see this as having two parts. A part on the outside of the parentheses and a piece that's inside the parentheses. And if you take a look at the piece on the inside, if we were to take the derivative of 4 plus x to the third, then that would give us 3x squared, which is a match for what you see on the outside. Okay, so what we're going to do is let that piece on the inside be u. So we're going to write let u be equal to 4 plus x cubed. Now in general, you're going to let u be equal to what's inside the parentheses, but that's not a hard and fast rule. Okay, all right. So since u is equal to 4 plus x to the third, then that means that du, the derivative of u, would be equal to 3x squared dx. Because on the right-hand side, we're taking the derivative with respect to x. So we're not writing it du over dx. So we have 3x squared dx. Now if you go back up to the original problem, notice that there's a 3x squared here and a dx here. Those two things together are going to get replaced by du. This piece that's underlined in green here is going to get replaced by u. So now we're ready to rewrite our problem in terms of u. Okay, what it's going to look like is the antiderivative, or you could say the integral, and we're going to replace 4 plus x cubed to the fifth with u to the fifth, and then the 3x squared and the dx are going to get replaced by du. Now we have something that we can take the antiderivative of. By the way, we didn't want to take the antiderivative of the original equation because this was raised to the fifth power. I really don't want to do 4 plus x to the third times 4 plus x to the third 5 times. That's a whole lot of algebra. You can do it, but it's going to get really big, really messy. Way simpler to do it by substitution. Okay, take the antiderivative of u to the 5th. So it becomes u to the 6th over 6 plus c. And now what we want to do is substitute back. All right, take and plug that 4 plus x to the 3rd back in for u. So we have 4 plus x to the 3rd all raised to the 6th all over 6 plus c. And you can leave that as your final answer. It's also pretty common to write it as 1/6 times the quantity of 4 plus x to the 3rd raised to the 6 plus c. Okay, we can check our differentiation with the chain rule. So we have 1/6 times 4 plus x to the 3rd raised to the 6 plus our constant c. So we're going to take 1/6. We're going to multiply by that exponent, so bring that exponent out in front. You keep the base the same, reduce that exponent by 1, and then multiply by the derivative of the inside, which would be 3x squared. The derivative of the constant goes to 0, and then we simplify. 1/6 times 6 will just reduce to 1. I'm going to bring this 3x squared out in front and leave the 4 plus x cubed raised to the 5th. And if you take a look, that matches our original problem. Okay, in our second example, we want to take a look at what's inside the radical and what's outside. And I'm thinking already that if I take the derivative of x to the 5th plus 8, that'll give me 5x to the 4th. So it's close. It's not exactly what we see on the outside, but I'll teach you how to deal with that in a second. All right, so we're going to let u be equal to what we see inside. So let u equal x to the 5th plus 8. That means that du, when I take the derivative of both sides, it would be equal to 5x to the 4th dx. Okay, we have the dx taken care of right here. Right, it's a match with what we have here. And we have the x to the 4th. That's a match. But we just want x to the 4th dx. Okay, so what we're going to do is divide by 5. So we're going to write du divided by 5 equals 5x to the 4th dx divided by 5. So we're going to write it as 1/5 du equals x to the 4th dx. Okay, so now we're going to rewrite our original equation, our integral, in terms of u and du. Okay, so in place of the x to the 4th and the dx, right, we're going to put in 1/5 du. So the du is going to go at the end of the problem, and we're going to put in the 1/5 because it's a constant right out in front. Okay. Next, we're going to replace the u. We're going to plug in u in place of x to the 5th plus 8. So we can rewrite this as the square root of u. Okay, now we're ready to integrate, but we do want to rewrite it as the 1/5 times the antiderivative of u to the 1/2 du. Okay, apply the power rule. We'll have u to the 3/2 divided by 3/2 plus c. Okay, so you have to clean it up because we have the 1/5, we have the 3/2. So we have 1/5. We're dividing by that fractions. We want to multiply by 2/3. And then we have u to the 3/2 plus c. Okay, multiply those fractions together. We get 2/15. And then we have to plug back in x to the fifth plus 8 for u. So it'll be x to the fifth plus 8, all raised to the 3/2. And again, don't forget the plus c on the end. You don't have to rewrite it as a radical. As long as it has a positive exponent, this can be your final step. Okay, in our third example, I notice what's inside the parentheses is 2x to the fourth plus 5. So if I say let u equal 2x to the fourth plus 5, when I find du, it's equal to 8x cubed dx, because the derivative of a constant would go to 0, so the derivative of that 5 goes to 0. Okay, so we're really close. I have the dx right here, and I have x cubed, so that part's a match. Okay, but what I don't want is the 8 out in front, because I need to get a 5 out in front. So what we're going to do first is divide by 8. Whoops. So we're going to end up with 1/8 du equals x to the third dx. Okay, so just hang on to that for a second. So in place of the x to the third and the dx, we're going to put in 1/8 du. All right, remember that constants can always be pulled out in front. So this 5, we're going to rewrite it right in front of the integral sign. So pull that 5 out in front. Antiderivative. Okay, so the 5 is taken care of. The x to the third and the dx are going to be replaced by 1/8 du. So I'm just going to put 1/8 right here for now. Give myself a little bit of space and put du in there. Okay, right in the center, we have 2x to the fourth plus 5, all being raised to the third power. So remember I said let u equal 2x to the fourth plus 5. So really we have u to the third. Okay, before you integrate, pull that 1/8 out in front of the integral sign as well, because it's another constant or another coefficient. So we will have 5/8 times the antiderivative of u to the third du. Okay, now you're ready to take the antiderivative using our power rule. So we're going to be multiplying 5/8 by u to the fourth over 4 plus c. Okay, multiply those fractions together. So you get 5 over 32. And then we're going to replace u with what we set u equal to in the beginning. So take u out and put 2x to the fourth plus 5 back in there. And again, don't forget about your plus c. And that's going to be our final answer. Okay, with trig functions, we're still going to think of our two pieces as like a part that you can take the derivative of and get the other part. But we're going to do a little bit of rewriting first. I would suggest rewriting this as the antiderivative of the quantity sine x squared cosine x dx. All right, if I take the derivative of sine, I do get cosine. Okay, so in this particular case, I'm going to let u be equal to the sine of x, and that means that du would be equal to the cosine of x dx. And just a little reminder, if you start with sine, the derivative is cosine. The derivative of cosine goes to negative sine x, and the derivative of negative sine x would become negative cosine x. So that's taking the derivatives on the left. For integrals or antiderivatives, you go up the chart. Okay, so u is equal to sine x. So we're going to take out sine of x and put in u. Du is equal to cosine x dx. So this whole piece, cosine x dx, is going to get replaced by du. So our problem now becomes the antiderivative of u squared du. All right, so now take the antiderivative, do u to the third over 3 plus c, and then plug back in what we set u equal to, which was sine of x. So we're going to have sine of x raised to the third over 3 plus c. And you could keep it written like that, or you could write it as sine to the third of x over 3 plus c, or you could write it as 1/3 sine to the third of x plus c. Okay, any one of these forms is fine. Okay, one more example. Okay, so because we have this 2, the antiderivative of 2 secant squared x times the quantity tangent x plus 3, I'm going to encourage you to rewrite it first as 2 antiderivative of secant squared x tangent x plus 3 dx. All right, so now in this case you might say, well, I don't know if I should think of the secant as the u value or think of the tangent as the u value. So I'm going to do a little bit of work off to the side, just kind of working through this. So if I say y equals the tangent x, I know the derivative would be secant squared x. Okay, if I said y equals the secant x, the derivative of that would be secant x tangent x. And I don't see that anywhere in the problem, so that's not the direction we want to go in. Okay, so we're going to let u be equal to tangent of x plus 3. Okay, so let u equal tan x plus 3. That means that du will be equal to secant squared x dx. All right, so let's check it out. So we have secant squared x dx. So I see secant squared of x, and I see dx. So those two things together are going to be replaced by du. All right, and then we have tangent of x plus 3 in the parentheses. That's our u value. All right, so we can rewrite the problem as 2 times the antiderivative of u du. How simple is that? All right, so again, we had all the pieces taken care of. We had the constant out in front. So the antiderivative of u, well, 2 out in front will give us 2 u squared over 2 plus c. And this gets cleaned up because you have these 2's. So we're going to divide out those 2's, and then we're left with u squared plus c. Go back in and replace u with what it's equal to right over here, just tangent of x plus 3. So our final answer will be tangent of x plus 3, quantity squared plus c. No need to expand that and multiply it out. All right, good luck on the homework. Make sure you keep asking me questions, okay?